With nails, we have the option to physically count them out. With atoms, we don't. They're too small to count. So we have to use the mass in order to count them. I think this is interesting. If you could see atoms, and if you counted them 24 hours a day, as long as you lived, you would barely begin to count the number of atoms in something as small as a grain of sand. Does that blow your mind just a little tiny bit? We can't count them. There's just no counting them. They're just way too numerous. So we use mass to count them. It saves a lot of time. So dozen was useful for counting nails. It's useful for counting hamburger buns and donuts. It's not very useful for counting atoms. So we need a bigger number because atoms are so small and there's so many of them. And so this is the number. Let me introduce you to Avogadro's number. 6.022 times 10 raised to the 23rd power. That's a big number. That's a 6 with 23 zeros behind it. Off the top of my head, I don't even know, millions, billions, trillions. I don't even know the name for a number that large. Cajillion, maybe? I don't know. Bazillion, that's probably it. So that's Avogadro's number. It's named after Amadeo Avogadro. He was actually born the same year as our country, lived to 1856. So this is the number, just like a dozen is 12 things, we use this number of things. And there's a reason. We didn't pick some arbitrary, strange number. Instead of calling it a dozen, we call it a mole. M-O-L-E. That word is used for several other things. It's a small, furry, short-sighted animal that burrows in the ground and wrecks your lawn. It's also mole, a tasty sauce to put on your chips. But this is the chemist's mole. And we sometimes refer to it as the chemist's dozen. It's a very important concept in chemistry. And it's one that can take a little while to get your brain around. If you think of it as the chemist's dozen and treat it like we treat dozen, that'll help. The mole is just a number of things. Okay, it's not a mass, it's not a volume, it's just a number. It's this particular weird number. So mole is a short unit. It only has 4 letters, and yet we still have an abbreviation for it, MOL. So MOL is the abbreviation for mole. So 1 mole is 6.022 times 10 to the 23rd things. This quantity is a reasonable number of atoms, ions, or molecules. This is a picture of 1 mole of copper atoms in the form of pennies. You can hold that in your hand. It's large enough to see, but not so large that it's difficult to handle. 2 regular-sized helium balloons contain 1 mole of helium atoms. 6.022 times 10 to the 23rd helium atoms. So this is a useful size for us to deal with. The numerical value, the 6.022 times 10 to the 23rd, came about as being equal to the number of atoms in exactly 12 grams of pure carbon-12. Now, I don't expect most 3A students to really get their brain around that, but some of you will. So, how much does 1 atom of carbon-12 weigh in atomic mass units? It weighs 12 atomic mass units. The definition of the atomic mass unit was 1/12 the mass of a carbon-12 atom. So a carbon-12 atom weighs 12 atomic mass units. And a mole is the number of carbon atoms in 12 grams of carbon-12. And what this allows is a relationship between the mass, in other words, the grams of carbon, and the number of atoms, which is Avogadro's number. And this is what allows us to count atoms by weighing them. So when we convert between moles and number of atoms, it's the same as converting between dozens and numbers of objects. So a dozen equaled 12 nails, and we did a problem like that, and that wasn't too bad. We're not even talking about the money part here. We're just talking about the dozen and the number of nails. We can do a very similar thing with a mole and Avogadro's number of atoms. So convert 9.5 times 10 to the 27 atoms to moles. So we're just going to use dimensional analysis here. We're starting with atoms, and we're going to moles. This is going to be a one-step conversion. So I'm going to write the number 9.5 times 10 to the 27 atoms. I have one arrow. I have one conversion factor. I'm going to have moles on the top and atoms on the bottom. And the atoms are going to cancel out. The relationship between moles and atoms is always the same. Just like the relationship between numbers of things and dozens is always the same. How many donuts are in 1 dozen donuts? 12. How many pencils are in a dozen pencils? 12. How many students are in a dozen students? 12. It doesn't matter what the object is, a dozen is 12. It doesn't matter what you have a mole of, the number is 6.022 times 10 to the 23rd things. So 1 mole is 6.022 times 10 to the 23rd. That number is one of the biggest reasons that you have to learn how to enter numbers in scientific notation on your calculator. I have yet to see a calculator that has a display that will accept 24 digits. And who wants to count 23 zeros as they type them all in anyway? So do this on your calculator. Remember that you're going to use the EE button or the EXP button. And that stands for times 10 to the. So on my calculator, these are the buttons I'm pressing. 9.5. My calculator has an EE button. Yours might have EXP. They mean the same thing. I'm going to press the EE button, and then I'm going to put in the exponent, 27. Don't press times. Don't press 10 or 10 to the x or anything like that. I'm going to multiply by 1. You can skip that if you want to. And then I'm going to divide by 6.022 EE23 and press the equal sign. And this is showing me 15775.48987. And the unit on that would be moles. Did your calculator give you that number? If you don't enter scientific notation correctly, when you divide, you actually end up multiplying by 10 to the 23rd instead of dividing by 10 to the 23rd. That's a horrendously large error. If you're having issues with your calculator, please ask me. I am the calculator whisperer, and I can make your calculator behave. Okay? And if we can't, I'll help you jump on it and smash it. Well, what should we do about significant figures here? 2 sig figs. Because what we started with, 9.5 times 10 to the 27 atoms. Now, if you're smart aleck, you might say, well, yeah, but that's a counting number. Could anyone count that many atoms? No, not in your lifetime you couldn't. So it's not a counting number. 2 sig figs. Avogadro's number, we actually know it to more decimal places than this. It is not exact. As written here, it has 4. So the rule for multiplication and division is that we're going to keep 2 sig figs. Now, some of you are still doing some funny things when you round numbers. So I decided I need two significant figures. I underlined the second digit. What's the place value of that digit? Thousands. Okay, so if I ask you to round this number to the nearest thousand, are you going to tell me 16? Or are you going to tell me 16,000? It's 16,000, right? The 7 makes us round up. We're going to round to 16,000 moles. I don't know if that makes any more sense to you or not. I've been going around and around with my 5th grader about rounding and exponents. The other way is to look at this and say, okay, this is a place value larger than 1. When I'm rounding, I better put this in scientific notation first so that I don't do something dumb. So 1.5775, oh yeah, I don't need all of those, I'll just drop them off. 1, 2, 3, 4 times 10 to the 4th. Now if I round to that, I'll get 1.6 times 10 to the 4th moles, and I don't have to worry about putting zeros in there. Either of those answers is acceptable. Any questions? So let's do one the other way. How many gold atoms are in a pure gold ring containing 8.83 times 10 to the minus 2 moles of gold? Avogadro's number allows us to convert between moles and numbers of atoms, ions, or molecules. So we can do this in one step. We're going to go from moles to atoms. Because we know that 1 mole equals 6.022 times 10 to the 23rd atoms. You'll save yourself some time if you memorize that number. 8.83 times 10 to the minus 2 moles. I want atoms on the top, and I want moles on the bottom to get rid of them. So we've got some weird numbers here. We've got this brand new unit, but this is just dimensional analysis. You can even do dimensional analysis with made-up units like thingamajigs and what's-a-bobbers. You can do a problem like that. In fact, that might make a good test question. You just never know. 6.022 times 10 to the 23rd atoms per mole. Sometimes students want to put the number in the other place. Well then, remind yourself, this is like dozen. Would I put 12 dozen equals 1 object? No, the 12 goes on the other side. So it's like the chemist's dozen. So now we do this one. 8.83 EE minus 2, negative 2, times 6.022 EE 23. This is going to be a big number. Uh, 5.317426 times 10 to the 22nd atoms. How many sig figs should that number have? 3. This one has 3, and this one has 4. So I'm going to keep the 3rd digit there. The next one's a 7 again, so I'm going to round up 5.32 times 10 to the 22nd. You never have to worry when you're rounding in scientific notation. It's just decimal notation. Is that a reasonable number of atoms to be in a gold ring? Yeah. Avogadro's number of atoms, 10 to the 23rd atoms, is generally a size that you can hold in your hand. What if we came up with 5.32 times 10 to the minus 15 atoms? Would that make sense? No, because that would be less than one atom. Could you make a gold ring out of part of an atom? No, you can't do that. It's like you can't make a family out of a person's leg. You know, less than a person in a family. It just doesn't work, does it? So I just have to tell you a personal story about Avogadro's number. You may be aware that the math people celebrate Pi Day. 3.14159 blah, blah, blah is pi, right? So on March 14th, they make pie and they do fun stuff. And Star Wars people celebrate May the 4th. May the 4th be with you. Well, chemists celebrate Mole Day. Mole Day is October 23rd. 10:23. From 6:02 a.m. to 6:02 p.m. Because it's 6.02. So, yeah, that's okay. It's Mole Day. So, I am a chemist, and my husband is a chemist, and our fourth child was born on Mole Day. Right? And he weighed 10 pounds, and he was 23 and a half inches long. Yeah. The only thing cooler is if he could have been born at 6:02 a.m. or p.m. I missed both of those. It was more like 8:30 p.m., but, you know, we'll take him anyway. And we actually had a very brief discussion, probably 10 seconds. Should we give him the middle name Avogadro? No, he said no. So that was a good idea, I think. But anyway, Mole Day is pretty special in our family. Okay, so if we want to convert between grams and moles of an element, we need something else. We need the mass of a mole of atoms. For nails, remember, we use the weight in pounds of a dozen nails. So for atoms, we need the mass, generally in grams, of a mole of atoms. And this is called the molar mass. The atomic mass was the mass of an atom. The molar mass is the mass of 1 mole of atoms or molecules. And what's really cool, and this is where Avogadro's number, being the number of carbon-12 atoms in 12 grams of carbon-12, comes in. Because of this, the molar mass is numerically equal to the atomic mass. So atomic mass is in atomic mass units. Molar mass is in grams. So we look at the periodic table, and carbon, the element, has a mass, an atomic mass of 12.01 atomic mass units. That's the average mass of carbon atoms. 1 mole of carbon atoms weighs 12.01 grams. So the numbers under the element symbols in the periodic table do double duty. They tell you the mass of a single atom with an atomic mass unit. They tell you the mass of a mole, a chemist's dozen of atoms, in grams. Okay, before I talk about what this picture means, can anyone find the error in this picture? There's only 11 of the small nails. Really, people? And this mistake was in the 3rd edition of the book, and it's still in the 5th edition of the book, because I've been too busy to tell them about this. Yeah, there's only 11 nails, and the point of this slide is 12 nails. So, I'm going to fix it. Okay, now there's 12 nails. So why is this slide here at all? Here we have a dozen large nails, 12 nails. A dozen small nails, 12 nails, even though one looks like a ghost. Do you think these dozens weigh the same amount? No. The bigger nails are going to weigh more because each individual nail is going to weigh more, and so if you have a dozen of them, it's going to weigh more. The same thing happens with atoms. We learned when we studied atomic masses that atoms weigh different amounts, right? And so then if you have a mole of those atoms, just like a dozen nails, they're going to also have different masses. My iPad is freaking out again. It only does this in this class? Did someone put a hex on it or something? Oh, there we go. Okay. I don't believe in hexes. Okay, so this watch glass has a mole of sulfur atoms. A mole of sulfur weighs 32.07 grams. Over here, we have a mole of carbon atoms. The carbon atoms weigh 12.01 grams. That's less than half as much. Because carbon atoms themselves, one carbon atom weighs less than a sulfur atom. Does that make sense? So the molar mass is the mass of a mole. It's the same number as the atomic mass, but with a different unit. So 32 grams of sulfur is 1 mole of sulfur. If you look at the periodic table, the number under S is 32.07. 1 mole of sulfur is Avogadro's number of sulfur atoms. 1 mole of carbon weighs 12.01 grams. 1 mole of carbon is Avogadro's number of carbon atoms. Same number of atoms, the masses are different because the individual particles are different sizes, the sulfur and the carbon. And just for threes, here's lithium. 6.94 grams of lithium is 1 mole. So the lighter the atom, the less mass in 1 mole of that atom. And molar mass is the conversion factor that allows us to go between grams and moles. And it's right there on the periodic table. Let's calculate the number of moles of calcium in 91.4 grams of calcium. So there's only one number in this problem, 91.4 grams, and they're asking for moles. The conversion factor for this is the molar mass, and we get it from the periodic table. We can go directly from grams to moles in one step. So we put the units in, 91.4 grams times moles over grams, and get the units to work out. And then we need the molar mass. We look for calcium on the periodic table. And if we round it to 4 sig figs, we get 40.08. So it says 40.08 on the periodic table. What does it mean? It means that 1 mole weighs that amount in grams. So 40.08 grams is equal to 1 mole for this element. Another way we often write it is 40.08 grams per mole. This is like the 0.150 pounds per dozen nails. Okay? So 1 mole weighs 40.08 grams. So we've got 91.4 divided by 40.08. We're going to round this to 3 significant figures, 2.28 moles. 3 sig figs because this guy has 3 sig figs. Any questions? Let's do one the other way. calculate the number of grams of sulfur in 2.78 moles. So we're given moles, and we're asked to calculate grams. We can go between grams and moles, either direction, in one step. 2.78 moles of sulfur, and we want grams on top and moles on the bottom. Comes from the periodic table, 32.07. 32.07 grams is the mass of 1 mole. The molar mass is the mass in grams of 1 mole. The units work out. We have 2.78 times 32.07. This will also end up being 3 significant figures. I think I mentioned to you once in lecture that if you're not great with significant figures, a good guess is to round it to 3, because it ends up being that a lot in the problems, the way the publisher set them up. Any questions? Well, when we were talking about the nails, we used the mass to actually count the number of nails, right? Not dozens. And I said that we were going to learn how to count atoms by weighing. So that's what we're going to do in this example. How many carbon atoms in a diamond that weighs 0.58 grams? Let's just approach this using dimensional analysis. So I've got grams of carbon, and the question says, how many atoms do I have? Do you know the relationship between grams and atoms of carbon? Probably not off the top of your head. What did we just learn how to convert grams into? Moles. We could do grams to moles. Moles are like the chemist's dozen, right? So could we do moles to number of atoms? Yeah, we could do that, because that's going to be Avogadro's number. So there we have our path. So 0.58 grams of carbon. I'm going to start putting my symbol in there. Grams of carbon. And then we're going to go to moles of carbon. And then we're going to go to atoms of carbon. That's what our path told us. Then I'm going to put moles of carbon down here to cancel that one, and grams of carbon down here to cancel this one. If you're still struggling with dimensional analysis, the time to get help with that is now, okay? Because you're going to need it in this chapter and in the future. I'd be happy to help you. We've got GRASP tomorrow morning from 9 a.m. to 3 p.m. Plenty of people that can help with that. Okay, we got all of our units in. Now we need numbers. The number of atoms in a mole, that's Avogadro's number. Mole is like dozen. So you would say 1 dozen is 12 atoms. 1 mole is Avogadro's number of atoms. And it's just a really long number, even in scientific notation. The relationship between grams and moles we get from the periodic table. 1 mole is 12.01 grams. It's the number under the element symbol. Then go left to right, multiplying by the top, dividing by the bottom. You shouldn't have to write down any intermediate values. Times 6.022, EE 23. And how many sig figs is this one going to have? 3 is a great guess, not quite right. 2 this time. I didn't say it would always work. 2.9 times 10 to the 22nd. And the unit left standing is atoms of carbon. Well, my calculator says 2.9082098 E22. Different calculators have different ways of showing you that exponent, and so you need to figure out how your calculator is talking to you and interpret that. We would not want to put down 2.9 atoms of carbon, because well, first of all, you can't have 0.9 atoms, like you can't have 0.9 people, right? They're individual things. But a diamond that only had 3 atoms in it would not be visible. It's not a reasonable number. Any questions? That was finding atoms from a mass. This is turning the problem around, finding mass from number of atoms. So here we're given the number of atoms, and they want the mass. It doesn't particularly say which unit. So then we could pick a convenient unit. Gram is going to be a convenient unit. That's mass. Again, we don't know a relationship between atoms and grams directly, but we could put moles in here. We can go from atoms to moles using Avogadro's number, and we can go from moles to grams using the molar mass from the periodic table. 1.23 times 10 to the 24th He atoms. Unfortunately, there are no she atoms because that would be 3 letters, and there aren't any elements with 3-letter symbols. And then we're going to have moles on top and atoms on the bottom. And then we're going to have grams on top and moles on the bottom. Atoms to moles to grams. Atoms to moles to grams. These units cancel out. These units cancel out. Then we look for numbers. These numbers aren't given in the problem. Avogadro's number is one that you should store in your brain. 1 mole of anything is Avogadro's number of that thing. So 1 mole of helium atoms is Avogadro's number, 6.022 times 10 to the 23rd atoms. And then grams to moles comes from the periodic table, 4.003. And that's specific for helium. Then on our calculators, 1.23 EE24 divided by 6.022 EE23 times 4.003 equals, how many sig figs this time? 3. 8.18, and the unit is grams. Any questions? Yes?
So we're not working with a direct relationship. There's no direct relationship from atoms to grams. We always have to use moles?
There is a shortcut, and since you asked, I'll mention it. So if you don't like what I'm about to say, feel free to plug your ears and say la la la. We know that 4.003 grams of helium is equal to 1 mole of helium, and 1 mole of helium is 6.022 times 10 to the 23rd atoms. Well, this is scientific. Oh, the 8.18? No. So 4.03 is equal to 1 mole, and 1 mole equals that. Therefore, 4.003 grams is equal to Avogadro's number of atoms. So we could do it in one step, but I'm not choosing to do that with all the examples because most students aren't real crazy about that one.
So when do you use the
That's a good question. Why didn't I write this in scientific notation? If the question said express your answer in scientific notation, then you would have to. If it was a multiple choice test and it gave you all the answers in scientific notation, you'd have to know how to figure out which one it is. My rule of thumb is if I have to count zeros, I want it in scientific notation. So 8.18, that's a nice number. If I had 818,000,000 grams, I'd want that in scientific notation. Or if I had 0.0000818 grams. I really don't like to look at more than 3 zeros because it gets confusing, right? Your eyes start to move around, and I feel stupid when I have to get my finger or my pencil out and actually count zeros. That makes me feel dumb, like a child. So that's my guideline. Does that help? So I'm not going to put 8.18 in scientific notation. We could, and I would say that scientific notation is never wrong. This would be 8.18 times 10 to the 0 grams, which seems a little silly, but that's what it would be, because 10 to the 0 is 1. Any other questions? So think about this. So I showed you a picture of 22 pennies. 22 pennies is Avogadro's number of copper atoms. If you had that many copper pennies, it would cover the entire surface of the Earth to a depth of 300 meters. That's the length of 3 football fields deep of pennies over the entire surface of the Earth, oceans included. That's a lot of pennies, hey, right? Wow, just this number, you just can't even get your brain around how big this number is. When we talk about the national debt and they throw around numbers like trillion, which are hard enough to think about, this is way bigger than that. Think about a crystal of sugar, granulated sugar, 1 crystal. The mass of that is less than a milligram. The diameter is less than 1/10 of a millimeter. But if you took a mole of those sugar crystals, it would cover the state of Texas to a depth of several feet. 4 or 5 feet of sugar crystals. Texas is a really big state. It's a lot of sugar crystals. Okay, so I share that with you because I want you to understand how fantastically large Avogadro's number is.